All right, and like I said before, we're on section 45. I don't know if that's right. Yeah, I think I misspoke at least once before about what section we're supposed to be on. We're on section 45, so we're basically going back to kind of like natural language processing, NLP. I think we talked back at the way before the beginning of the module, like maybe like section 37 or something along those lines. So we're kind of going back to this, but this time we're applying deep learning specifically to natural language processing. So kind of like refresh yourself a little bit, like think back on like when we were doing things like, when we're basically creating back words, we're doing stemming, lemmatization. Basically you have a whole bunch of like corpus, which is basically a bunch of Word documents, like documents with words and sentences and such like that. So we basically have this already put together. And now we say, okay, what if we actually want to start predicting things on top of it? And so this is what today in next session we'll kind of talk about. But next session we'll specifically talk more about like other deeper learning models besides NLPs, something called recurrent neural networks or RNNs. So just kind of be aware like this kind of stuff can all be applied together. But we're going to start with the first part, which is going to be embeddings. So let me go ahead and start sharing my screen. Excuse me. All right, so let's share that. So now, right now, you should see embeddings. Of course, disappear for a second. Okay, cool. So, all right. So embeddings, I think we mentioned, correct me if I'm wrong, but like I thought we mentioned this at least briefly at the very first section in NLP. And I think I showed a little bit what I'm going to show today, which is Kaggle has a, what's it called? Kaggle has a resource here, a learning tutorial for embeddings. It's not NLP specific. It actually uses movie titles. There's also a similar thing with Google's embedding crash course here, which I think also uses movies as kind of like a reference. But no, the concepts of embeddings, they don't necessarily have to be natural language processing. It's just that it works really well for NLP. And the real reason why is because words by themselves don't have any meaning, because remember, computers really only know numbers and we can only train on numbers, right? So like just like with convolutional neural nets that we saw was a past few sections now, these ones you need to take your, like in the convolutional neural nets, you basically take your image and convert them into a set of numbers essentially and go off of this. So in the same way we have to take, for language, for words and stuff like this, convert them essentially into some kind of number. And so there's actually a few ways we could do this. Embeddings is what we're going to find out is actually much more efficient. But one really quick, dirty way to do this, which does not work well at all, kind of similar to how MLPs really do really bad with image detection, is we can just basically list all the words and basically one hot encode and say, okay, man, basically it's represented by the vector 1 and then a bunch of zeros. So if you have like, let's say a corpus of like 10,000 words, like your vocabulary is 10,000 words, you would have a vector that's 10,000, units long, 10,000 dimensions. And basically each word is represented by saying, oh, it's one hot encoded. Like, oh, it's man 1 and all the rest are 0. Or like it's woman, there's 1 somewhere at a different spot in the vector and then 0 everywhere else. And that could technically work. It's just that it's really poor at actually doing anything useful with it. Just like we saw with multi-layer perceptrons, basically our classical neural nets. We had to, for images, we had to basically take, instead of a vector of like all the pixels, we had to use something more complicated or more complex like convolutional neural nets. So that's kind of what embeddings does. Embeddings basically says, all right, like if you think, I like making this comparison, is that if you think like convolutional neural nets is taking the concept of like, it has just basically a bunch of pixels, like basically a bunch of numbers, and says, okay, I don't really care about the individual pixels. What I really care about are the grouping of pixels, and say, what do those represent? Whether that's an outline, an eye, a nose, an ear, or whatever, those different structures that are in there. That's what a convolutional neural net does. Embeddings basically try to do for NLP at least, but this also in general, is it's trying to find the context of what is going on between these items. So really what we're trying to do is we're converting these words into a mathematical object, and we're not just making it into a simple mathematical object like a vector, like with that vector with one hot encoding. Instead, we're basically going to make these kind of things called embeddings. And what's really cool about this, and you can see this diagram right here going on. I believe this came from Google Embeddings crash course. So I think that's where this one originated from. Could be wrong. But basically, it's that you can then take words and put them in a vector space. And you can actually, with vectors, you can imagine like moving in a direction. So it turns out you can basically have related things that are close together. So basically, the idea here is that in linguistics, there's this idea called the distributional hypothesis, which basically says words that are similar or have context are grouped together closer. So like, for example, if I said, oh, my dog is fluffy, well, fluffy and dog are associated in some context because of the fact that in the sentence, it's close together. The closer these words are together, the more likely they are related in some context. So that's kind of like the idea of this distributional hypothesis. So what's kind of cool though, is that we can use kind of the same ideas about closeness in like vector spaces and say, okay, well, basically points that are very close together in the vector space itself are in fact similar. And what's kind of cool on top of that is that you actually end up having this kind of like directional spacing too. So for example, this says man and king. So basically man and woman, they're similar in some way. They're like a person, right? King and queen, okay, person, but royalty. But you can notice that there's kind of this direction where like, okay, man and king, if we move to the right here like this in this direction, the same direction, we tend to get basically the female form of this word and vice versa. Moving to the left would get the male version of this part right here. And so this is where actually embeddings will naturally encode this information. So you'll see similar things grouped together, but also basically how words relate to each other, basically by using another vector to move across this vector space. So you can see here, for example, verb tense and then country capital, where essentially we can move off in one direction and we'll tend to get the thing that is like associated. Now note that we don't specifically say, oh, encode this information verb tense in this direction, which is the magical thing about embeddings. You don't have to actually say, oh, this is the pattern that you should be looking for. Essentially what happens is we're going to create this complexity and we'll see how we actually do this. So a couple ways we can do it. But basically we're saying, okay, define the context. And that's what this arrow really represents, is this different context to say how these things are related to each other. And you machine learning algorithm, essentially, you figure out how to find this context. And this is all comes down to the idea here. is the reason why we can do this is, again, because of the distributional hypothesis, is that context basically comes to the idea of how close things are. So yeah, that's kind of like an overview of what embeddings are. But really what they are, essentially, they're just they're vectors of context. So instead of having the vector of the actual item, it's a vector that contains some kind of context. So we're going to kind of talk a little bit about how we actually get this through here. So when I say vector of contexts, and I wonder if I'm trying to think if there's a good example, but I'm just going to draw it out. So I mentioned this last time. Like when I say last time, I mean like, was it probably like 2-3 weeks ago in the original NLP course or NLP section, is that if we have a vector, you can imagine, let's say like man or king. I think I shared it with movies. It's like each part of this vector right here would represent, like for a movie, like, oh, how action packed it is, right? This would be some number on here, like say 1 to 0. It's like, okay, that's how action packed it is. Is it a comedy, right? Or how funny it is. So maybe, for example, this movie, for example, has like, really funny. And then maybe something like next part is like romance, right? And it's like, okay, this one has like a 0.6 romance. So this was probably like a romantic comedy, but more on the comedy side of this, right? So this would represent a movie here. That's kind of what I showed before. So a similar thing happens with the idea of, with words, basically. So we can have an embedding. So this right here is an embedding. So we can have something similar with like a word, for example, let's say king and queen or something like that. You can say something like, oh, is it like male? Is it a noun? I'm trying to think of something like royalty, like they're basically these contexts. We don't really know what these things are. I'm just going to give you something so we can, like, as humans kind of understand it, but they basically would have also values, for example, to say how, male is it, or how, does it represent royalty, or is it fluffy, or is it, really scary, like these really like harder things to kind of, like, if you imagine we had to go through all the different contexts, it'd take a long time. And essentially we will design this ourselves, design the architecture to figure out this context for us. But the idea here is that all these numbers would represent some kind of context about this specific word, okay? So the way we do this now, there's one of the ways. We'll see Word2Vec and then later GloVe. And the first thing, let me just make sure I can point. Okay. So the first one right here is I really want you to focus on this part of this diagram. So this was showing actually how you can basically take embeddings, which basically your embeddings will be created right here, in this green right here. And then seeing how you can take this embeddings and basically train it as a bigger neural network. And this comes directly from this Google embedding crash course. But I thought it was a good diagram because right here is essentially, if you think back to what we started off with, you basically start off with a bunch of words, okay? So essentially we have is a one hot encoded words, okay? This long vector. So if you imagine a vocabulary of 10,000 words, you would have each word represented by one of those vectors because they're 10,000 dimensions, which is ridiculously huge, right? So what you basically do is you create a neural net. This is one way you can do Word2Vec. Essentially, you can say, okay, connect this neural net with these hidden layers in here, or this hidden layer. And basically, at the end here, this logic layer right here, basically saying like what the classification is. And what's kind of cool is you can basically teach it, and I'll tell you what this is in a second, but basically you can teach the neural network and say, okay, train this part right here to basically match these parts really well. And it seems like when you do a neural network, you would be training to figure out this classification. But really what happens, you turn out to know what this is. You turn it out on what the classification is. And it turns out what you really care about is the weights on this part of the layer, this hidden layer. And this ends up being your actual embedding code itself, or your embedding vectors itself. So it's kind of cool is that basically you kind of like not hijacked, I don't know if this works. Basically you kind of like make it look like you're training for one thing, but end up you really care about this hidden layer. Usually we don't even care about the hidden layers itself. We just care about the ending part. And essentially right here, we're actually getting the hidden layers directly so we can create an embedding. So that kind of description is Word2Vec. So I'm going to explain a little bit more of how that works. But so far, any questions on embeddings or just the general use of them? Very good, Nelson? Cool. All right. So Word2Vec. So Word2Vec is basically what I described, but we're going to go a little bit deeper. So we come up with something called a Skipgram model. And what we do here is we're going to basically design a neural network. It doesn't even have to be very complicated, but basically design a neural network to predict the words that are, basically what words can come around the first word. And so kind of going a little bit, I'll explain a little bit more about this, but basically you start off with a word here. So you can imagine like 10,000 words, this vocabulary, and it's one hot encoded, right? And then you have this hidden layer right here. In this case, it's like a 300 node layer. This will actually become our embeddings itself, okay? And then at the very end here, basically it's saying other words and say, what's the probability of landing? If you started off, let's say this word is like the word, hill. And say, okay, like, starting with the word hill, what words will come around hill? And it's like, oh, there's a probability of, let's say, 0.02 that it will be ant. And it'll be 0.0001, it'll be aardvark, right? And then we can go on, basically go through all the different words that are one hot encoded this side. So this will also be 10,000. And basically say, okay, what word, if there's a word here, what words would come around it? And so this is, you would train it and basically maximize and get this loss function. And you would maximize to the point basically where this neural network would hopefully predict close to the right accuracy of what you'd expect it to be based on your corpus. But what's cool about that, that will actually learn this context right here, this embedding layer. So again, to kind of repeat right here, these are kind of the different steps, is that we're going to train the multi-layer perceptron, right, MLP, our neural network, okay, with basically mapping a word to a word. So essentially, we're going to take a whole corpus, and in this corpus, basically, what are the words that are close by it, and we're going to predict those words around it. But since the words are really close together in context, just like the distribution hypothesis kind of says, we're really teaching context. And we're saying, okay, basically, without ever saying what context is, basically we're saying neural network, figure out what the context is to know how to map it over. And that's what this embedding layer represents. So the idea here, like I have a little example. It's like a fluffy dog is a great pet and a fluffy cat is a great pet. Cat and dog have similar context to each other because they're interchangeable. These words, these fluffy, great, and pet, okay, those things are likely to come in about the same amount of probability as each other. So in some contexts, dog and cat are very similar. In other contexts, they might not be. For example, if I said like feline, dog is very unlikely, it's less likely at least, than cat to show up. So it's a different context in that sense. So we can kind of build this up. So this is kind of the idea of what we're really kind of like trying to build is like, we essentially are training to have it map our one word to words that are around it and grabbing it from the embeddings. So kind of to go a little bit like, how do we get this part? Like, how do we get this lost part? What we can do basically is in our, what's it called? When we actually like go process the data, right? We basically have this huge corpus of like all these documents, right? All these sentences. And so for example, this sentence right here, a fluffy dog is a great pet. For example, it would basically say, okay, well, fluffy and dog would be an element. Okay, and then also great and dog would be an element. Okay, and then other things, pet, right? And dog is an element. And basically we would basically count out all of these things, like for dog, so given dog, how often does pet come up? How often does great come up? How often does this happen? And that's the probability right here. So we'd find out like, oh, fluffy, when dog, given that dog happens, the probability of fluffy happening is like 0.22, right? So that's the probability of happening. So that's how we would compare it over here. It's like, okay, well, this should be 0.22. And if the vector comes out here from our first initial training, it's like, oh, it came out like 0.8. It's like, okay, we need to adjust this. We retrain it, basically train these nodes out more and go through it. But then we don't do it just for one word for dog, we do it for all the different words. And this is why it's so powerful. Basically, it's maximizing, or I should say it's minimizing its cost by changing these weights over here, okay? So that's really how Word2Vec works, Skipgram model. You can think, the reason that's called Skipgram is basically you can think of it like it's saying what are the things that are related outside of this. It's kind of skipping over and it's like, okay, like these are the parts that really matter over here. And this is our target word right here. But in this case, dog is our target word, but essentially for the whole corpus, we do it for every single word. So fluffy would be our target word and great would be a target word and pet would be a target word. And basically would build all these parts so we can get this whole context, just so we can get this embedding layer. Okay, so you can see we can actually decide however big we want this embedding layer to be. If we have more nodes in this hidden layer, the more complex our context will be. But also, it would take a lot long. It will take long. Well, it could take a lot longer, right? The more complex it is. So these are like some trade-offs and stuff. And in fact, you can imagine very, very large corpus, corpi, I don't know, but corpuses, right? You would take this and you might have a very, very large embedding. Like maybe you have like a few hundred, you know, for embedding. But compare that to something like could be possibly like tens, if not hundreds of thousands of different words. That's a huge reduction in dimension, right? Versus like something that's like, think of every word in the English language, trying to train on that and say what the context is. That would take a long time for us to input this whole vector. They become very sparse, basically. There's basically a bunch of zeros. So we can take this and kind of condense it down. So embedding in a lot of ways a dimensionality reduction, okay? But usually we talk about it for words and stuff, but it can be done for other things, like I mentioned about for movies and such. Okay, so that's Word2Vec. Any questions on that? Cool, all right, looking good. So another strategy we can do, another method is GloVe. And so the curriculum doesn't go into full details of what GloVe is. GloVe basically global vectors for word representation. I believe it was developed by a group in Stanford. And basically what's kind of cool about all these stuff is that we can actually use this model and like someone's already built this model and we don't have to do it. So you think about it like embeddings itself for like, what's it called? We'll talk more about this, but basically embeddings themselves don't really change. Like, you know, like English itself, probably like if you use a whole corpus, the context probably means the same. There's some cases where that's not true, like it's a specific context, like medical terminology, but the idea here is that you don't have to change it. So the curriculum actually uses GloVe as like the model is already pre-trained, but it's important to know like how they even came about this. So one way you can do this basically is that they create a matrix of probability of what word WI, okay, in context of the word WJ for a whole corpus gives us a probability. So what I mean by this, it kind of goes through, is basically we have on each part of this vector. So right here you can see like our words. Essentially what we have is this big matrix where we have like each word I, okay? So let's say we have like 10,000 words, right? So each word is listed here on this matrix, right? And then on this part, we have word J, okay, WJ. And this one has the same words, right? All 10,000 words again over here, okay? And basically what happens is that if you were to cross over, it's like, okay, from this word here, let's say this word ant and this word like hill, the probability here is just how many times does this, well, not probably many times, but it's the probability, what's the frequency of this word showing up in the corpus? Okay, so this could be a collection of documents. So like how many times, every time you see ant, how many times does hill also appear? And that would give you some probability. And they basically, that you do that for each individual word and you build this whole matrix, okay? And this right here basically will build you a context matrix essentially. It says like, okay, like this is our different, what's it called? This is like how often things happen, because the idea is like if they happen very frequently, they probably have similar context to each other. And basically it's like, okay, like we need to figure out though what these values are for these WIs and such, right? And essentially what you do, you then train this on a neural net to figure out the best way to put these values in here so that they actually match out to the probabilities within here. And essentially you create this new word context concurrence matrix, which is a mouthful, but like the idea here is that basically this holds the context of each word. So what's kind of cool about this is that you don't actually have to, like, again, it's kind of like you're training the network to figure out what the context is without you having to do it. Basically the weights for each of these words should have different weights. And you can imagine trying to make these probabilities all within here by adjusting every individual weight would take a long time for you to do yourself. And the idea here is you use a neural network to basically maximize the loss, I should say the cost, or say minimize the cost between these probability points and what actually happens in the actual corpus, okay? So that's another strategy. And it's a little, you can see it's a little bit different than getting this hidden node layer, but it essentially achieves a similar kind of concept, is that we basically create this matrix here of these features of content. And then we can actually use that to apply it to other, I think I'm highlighting the wrong one actually, I'm sorry. It should actually be this one right here, is this right here. It's your features and context. Basically your words and what the context is. We can multiply it by what we actually have, and we can actually get the concurrence matrix for new sets of like a new corpus. Okay, it's cool. So these are two ways to get embeddings, and it just gets your different embeddings, these different rows. So you can imagine here is that this row right here for this concurrence matrix, this is the actual embedding itself. So like for the word ant, it will have this context that goes right across here. Okay. So any questions on GloVe? Okay, cool. Again, the curriculum really shows it more like as like, oh, you can use this, like you don't really do it yourself. It's more like, oh, you could use this kind of thing. Just be aware of that. So once we have the actual vectors, it kind of comes down to like, what do you do with it, right? So one thing we can do is the genism, I actually don't know how to pronounce this. I just always write it out, but genism, I'm gonna say genism library can help you basically do a lot of things. Like for example, can actually help you build these vectors. Another thing it can do, it can help you visualize them, not visualize, but help you explore a little bit how these vectors work. So the main thing here is like the curriculum kind of goes to this, but I kind of want to repeat it here. As you can see here, it's just a different library. We're importing Word2Vec, so remember that's the strategy right here. So we take Word2Vec, and I think this comes directly from the curriculum itself. So we do a Word2Vec, we take our data set, right? Basically all the sentences, we feed that into here. We say what the size of like, what, how big of a embedding we want, right? Do we want it to be 100 dimensional, 400 dimensional? In reality, I'll tell you is that for your own use, you probably, unless you have a lot of time on your hands or really good hardware or like something in the cloud, this size would be, as you get bigger and bigger, the longer this will actually take to figure out. Basically, this is the size of your embeddings, okay? Your window equals 5. The curriculum kind of shows this, but basically you can imagine like your window as being like how many words around do you see? So for example, like if dog is my target and that my window is like, let's say 2, you might only get the first 2 words that are around it, okay? So it means that you really focus in. So if you make your window very, very large, for example, let's say your window is like, I don't know, like 10, you'll get all the words around that target word, but those words might not be the same context. Remember, the idea here in the distribution hypothesis is that if you get further and further away from a word, basically, the less context it actually is associated, or the less it's less associated with that word, which kind of makes sense, hopefully. So in this case, usually about 5 is about a good number to kind of go around. It's not too many words, but it's not too few words where you're missing some of the context, okay? And then this minimum count basically is, here, yeah, I want to make sure this works. Okay, it's basically like how often, like only count the words that show up often enough. And this doesn't include stop words because at this point we should have already filtered out the stop words for data. Okay, but the minimum count basically is like we're trying to avoid things that are very, very rare words, which kind of makes, hopefully that makes sense, is that just like if you learned a new word, if you only see it used one time, there's a pretty good chance you'll miss like the context of what that word actually means. You probably have to see it a few times, or you have to go, you know, in the end, look up the dictionary. But in this case, we don't have a dictionary. Essentially, we're just basically trying to figure out the context ourselves. So if we only see it a few times, it might not be worth keeping because we will probably get that context wrong because it only comes up once, okay? And then this last one right here, workers for, this is more like the hardware side of like when you're training. This stuff is more like the meta stuff saying, okay, like how big should the vector or embedding be? You know, how many words should we look at? You know, what words should we exclude? You know, the data set itself. This workers for comes down to how many tasks basically can be run at once. And so we call this basically the number of threads. It's kind of, it's not exactly right because workers, you can have multiple workers per thread, though usually you don't want to because as we talked about before, oh man, I don't remember exactly when, but when we talked about distributed computing with CPUs, is that if you have too many workers essentially on one thread, you have things like thrashing where you basically are doing all this work on the CPU, but it can't get there fast enough. So usually we basically come up to about how many cores there are. So if you have 4 cores, quad core, you use 4. If you have a 8 core, you use 8 cores. Note that that's not always true because you also can have like hyperthreading like in Intel cores. So like Intel core processors, like if they have hyperthreading, so for example, some of them have like 16 threads, but only 8 cores, you could have 16 workers then because there's 16 different tasks that can be independent from each other. So the idea here is that basically how efficiently can you split up the work? And then we actually do the training. So this model.train basically will train on this using this Word2Vec, basically this structure, right? And basically here you can see total examples. You basically just have this corpus already put together, okay? So that's kind of the idea here. Let's see here. Okay, so one other cool thing about Genism, we can also do things like analogies. I think I showed this about last time, but like we can do things like if this is to that, what is this to this? So like I think I showed about from this Kaggle tutorial right here. Basically, you can do things. Let's see here. Okay, cool. So in this case, they had it for movies. So in this case, you can see like, for example, what movies are similar to other ones. So for example, in this case, like, oh, what's the most similar to Toy Story? So we can have something similar as like, you know, what's the most similar to like the word king? And you might see things like, you know, queen, princess, prince, castle. You might see things that are similar to each other in that way. And you can see this value that goes through here. Also note that I didn't mention this, but when we say things are similar, it's about how close they are. We can use different ways to measure that. One of the more common ways to use this is the cosine similarity, but you could also use the Euclidean. The reason I use cosine similarity is because cosine represents about vectors being similar to each other. Basically the angle between those two vectors, since all vectors start off essentially at the origin. And so cosine similarity is usually used, which goes from -1 to 1, but usually we'll adjust that to go from 0 to 2. So just kind of know that you'll see that difference going on. But you can see here, they said most similar. This is just using the Genism, why not? That library. Do you know how it's pronounced?
I'm trying to think. No, I don't think I do.
Okay, yeah, Genism. I'm sure they have it on their site or something that's pronounced. I never say it though, so like I need to look this up ahead of time. But anyway, essentially you can use this library to say, okay, what's the most similar stuff? And then also, I'm trying to find it. Here it is. Okay, you can do things like, you know, it's kind of funny. Here they call it semantic vector math. So you can say, for example, in this case, it's movies. It's like Scream is equal to Psycho plus something. And so you can actually say, okay, Scream is the positive part. So you can say Scream is positive minus Psycho, which is in this case in their model, and say, okay, what's the missing part, right? What's this part right here? And the missing part you can see here is like Scream 2, Freddy versus Jason, Final Destination, Booty Call, Charles Angels, Mortal Kombat. You're like, wait, like why are these things showing up? And this person kind of says, oh, because Scream is a comedy. So basically, the thing missing between Scream and Psycho is that there's comedy right here. So you can imagine like Psycho plus some comedy movie is equal to Scream, because Scream is kind of like a scary movie, but also kind of funny. So you can do something similar with words, where you can say, okay, like for example, if I had like let's say king, and I had like queen here, the missing part, as you might guess, is like female or something that's female, right? It's like, okay, well, if you add the female aspect in that sense, we would get like queen. And so that's the same idea from the very beginning here, is that we essentially are doing this part. It's like, okay, we start off with man. Let's say we start off with king, we end up with queen over here. What's this missing part right here, this vector? It's basically something that says this is female, okay? So you can kind of do some interesting stuff, and it's a good way to kind of do a gut check of like, does your embeddings work really well? Or you can basically find other related items. This can be really useful. For example, if you're coming up with language, or like, let's say, for example, slang, for example. Slang might be really difficult for you to actually parse if you have never seen it before, or basically maybe another dialect. And you can basically say, okay, like, well, let me see, if, let's say this word or whatever, it's like, well, this word is related to this word in this way, and I know what the context of these are, but now I have this word, this slang word, what is this related to this context? And you can actually find those kind of similarity stuff and see the relationships. So it can be really interesting, and also just kind of fun in general, just to see what kind of pops up. Okay. So I'm gonna skip over TSNE in a second, because this isn't talked about in the curriculum, but I thought it was an important one to kind of check out. But I did want to mention about transfer learning first, because that is talked about in the curriculum. And I kind of mentioned it a couple times with like GloVe. Basically, transfer learning comes to the fact that your embeddings are usually hundreds of dimensions. But the problem is that like doing hundreds of dimensions for a very long, you can imagine this like neural network being very, very large just for like, Word2Vec. Can be very large and take a long time for it to train. So what you can do is basically take someone else that has another model that has already trained on this stuff, okay, and apply it to your model. So you can really think of it just like, CNN transfer learning, is that basically we're taking the model that someone already developed and we're just going to pass our word through it. And the reason why this works is because you can think of it is that the words that we're using in English are more or less the same context, no matter, what document we're talking about in it, right? Dog, and cat usually are meaning like, pets in some way. So we already have that incorporated in it. Note, however, is that if it's very specific terminology, you have to be very careful about this, because if, for example, let's say it's medical terminology, like these words that you're using might not carry through with the same basically context. And this again actually comes with the fact, like with slang, is that if you have some other slang or other, but basically slang might not, I don't like using that word because it makes it sound like it's not correct. But like if a demographic is using a certain like way of speaking or whatever, or think of even like teenagers or texting, like LOL, for example, might not appear in like classic text, which you might train on. So it wouldn't do very well on using those embeddings that were trained on classic text and stuff like this. Also, there's a recent there have been some recent research that shows, for example, a lot of these pre-trained models do very poorly on specific ethnic groups in the way they speak online. And so it's actually a really interesting part where you have to consider, well, okay, does this actually apply to the thing I'm looking at? So one example of this was, for example, a part of Twitter called Black Twitter, basically. And basically like the way people would kind of communicate on that. And it's not very different, but like they use different terminology and stuff that just was not included in the data set originally, which again comes down to the fact that it's not about your models, if they're biased or not, because your model will find the optimal thing. It's all about the data. If your data doesn't include certain parts that for whatever reason, whether it's because you were unaware of it, because you thought it was unimportant, or you were only experienced with this part of like this set of corpus, right? For example, if you only looked at classical literature, you now have a bias in your model because you only looked at classical literature, because people don't write online the same way people write in classical literature. So those are the kind of things that you have to kind of consider. So again, transfer learning is really great because you don't have to train it yourself, but just be aware that if it's very specific terminology, it might be best to look at other methods and stuff, or at least be aware of those methods and test it along, the specific terminology that you're concerned about. And if you don't see it, you might have to honestly, like there's a lot of places where NLP just is not up to par in that level of like, different ways of speaking. So be aware of this. So anyway, that's transfer learning. Any questions on that? Okay, sounds good. Okay, so last part I wanted to mention before I finish up is TSNE. So T distributed stochastic neighbors embeddings, which of course is a ridiculously long thing. We just call it TSNE. Again, I never like pronounce this out, but thankfully they're just letters. So just know it's kind of like another way of doing dimensionality reduction, just like PCA. However, I think it's even cooler than PCA because what it does, it tries to maintain the relative distances. So this works really, really well for like words, like the way we're describing embeddings, because our distances and basically how close things are together are really important for embeddings. Basically, when things are really close together, that means they're related. So TSNE basically tries to keep these distances, but allows you to visualize it. So again, from that same tutorial through Kaggle, basically they have talked about TSNE. I think it does a really great job showing this kind of stuff. Again, in context of movies, but basically you can use this to help visualize some of your data. So for example, you can see here all these different data points in 2 dimensions, which again, think about this. We're taking something that's at least, I can't remember what their original dimensions were, but I think it was 8 dimensional. Maybe it's, I don't remember what the dimension was, but whatever the dimensional size was, oh, here it is. Is it 2 dimension? Oh no, okay, this is, okay, sorry. I don't know what the original dimension is, but basically they reduced this dimension into 2-dimensional, which is much easier to find. And you can see basically each data point here represents a movie, and you can see there's some clustering and stuff like this that kind of goes around. And they actually kind of started exploring it. For example, they looked for Harry Potter and they found Harry Potter here, and they zoomed in. And when they zoomed in, they can basically see, I don't know, well, you can see that, but oops, too close. You can see here is that Harry Potter, basically all the other Harry Potter movies are there. I think I showed this last time, or way before. But all the Harry Potters are clustered together. But also you can see like Hunger Games, and Hunger Games. And so you can see that's kind of similar. It's like, okay, they're also series. They're also, maybe like roughly, related in that way, maybe because of the same year they mostly, maybe it's because it's like more focused toward teenagers and stuff like this. Maybe that's one of the reasons why they're clustered together. So you can start seeing a little bit of how close things are without actually having to go through every individual number, for example, calculating the distance between the two with their cosine, or trying to visualize a very high dimensional data set. Remember, we can't do that. So TSNE is very, very nice to be able to help visualize these different structures without completely changing over the distances. So really useful thing. And also note that they can also be really good for images as well. So you can basically see how well, like how close images are related to each other too. So you don't necessarily have to have it for word embeddings, but also for image embeddings. For example, how related are these kind of items in here? So I thought that was a really cool thing. So just link that in here. Cool. All right. Oh, another part I kind of mentioned is that it can help you identify relationships, but also help you find bugs. So if you find, for example, that your thing is just not predicting on context, maybe you need a more nuanced context. Maybe you need, for example, a bigger embedding like a vector itself. So maybe higher dimensional to capture all the context that you're expecting. So again, really, really useful to actually do. Cool. All right. Yep. So that's kind of all this is that I have for embeddings, which again, a big part for NLP. Next time we'll talk about basically ways to apply these. For example, recurrent neural networks, LSTMs and GRUs. Basically, these are ways to improve on our neural networks to predict on top of these, especially for NLP, because this context is so important. We have to kind of approach it in a different way than our classic MLPs. Okay. Cool. Any questions?
Okay. No, I think I'm good.
All right, cool. So I'll go ahead and stop recording then.